We've been deriving in class a formula for the Fourier transform of a function, and what I'm going to do in this video is run through an example where I compute a Fourier transform for a function, and then I'm going to show you what that Fourier transform does and what it looks like. So the function we're going to use is the function f that's going to be 0 from -2 to 1, and then 1 from 1 to 2. So this function is only defined on the interval from -2 to 2. And if you've been following the notation we've used in class, that means that number p is 2. So here's a graph of the function. Again, it's 0 from -2 to 1, and it's 1 from 1 to 2. So this is a piecewise defined function, and an example that we will use commonly. So when we say we're going to compute the Fourier transform of this function, what we mean is we're going to write f as frequencies of cosine and sine, and this is the 0 frequency out here. And what we're computing is the AM and the BM and the A0, and those are the amplitudes for those frequencies. So we have here the formulas that we've derived in class for computing AM and BM and A0, and I'm going to go through and compute those. So A0 is 1 over p, the integral from -p to p f of x dx. That's just a definition for A0, or I guess the formula that we've derived. In this case, we've said that p is 2, so we're going from -2 to 2 f of x. And then remember how f of x was defined up here. It's defined in two pieces, from -2 to 1, from 1 to 2. So we're going to split this integral apart over those two pieces, an integral from -2 to 1 and an integral from 1 to 2. And on this first piece, from -2 to 1, that function is 0, and then from 1 to 2, the function is 1. So we end up with just an integral of 1/2 the integral from 1 to 2 of 1 dx, which gives us 1/2. I need to do that. Okay, so we've computed A0, and notice that that means that the function f starts with A0 over 2, or 1/4. There's a 1/4 here in the beginning, and we'll get to that in a second. Okay, now we're going to compute A sub m. So this is the amplitude on the cosine frequency, and we have a formula for that. It's 1 over p, integrating from -p to p, the function f cosine m pi x over p. Plugging in the fact that p is 2 into that integral, and then doing the same trick that we did before. Because this is a piecewise defined function, we're going to have f as 0 on the interval from -2 to 1, and 1 on the interval from 1 to 2. So we split that integral into two pieces. And on the first piece, it's 0 for this function. So we're only going to integrate from 1 to 2, 1 times cosine m pi x over 2. Take the antiderivative, that's 2 over m sine m pi x over 2 from 1 to 2. Plug in 1 and 2. And when you plug in 2, for x, you get sine of m pi, and for an integer times pi, sine is always 0. So sine of 0 pi, sine of 1 pi, sine of 2 pi, sine of 3 pi, so on. Those are always 0. And then when we plug in the 1, we end up getting sine of m pi over 2, and that's actually 0 when m is even, and when m is odd, so for example, sine of pi over 2, then that's 1. If m is 3, sine of 3 pi over 2 is -1. So this thing, as m changes, when m is 0, we get 0. When m is 1, we get 1. M is 2, we get 0. M is 3, we get -1. It's going to alternate between 0, 1, 0, -1. So it'll go 0, 1, 0, -1, 0, 1, 0, -1, so on. But we don't need to know that. Anyways, so this simplifies down to this. Now we'll compute B sub m. Again, formula we derived in class, B sub m is 1 over p, integral from -p to p, f of x sine m pi x over p. P is 2. And because of the way f is defined, we're going to split that into two pieces. In the first piece, f is 0. Second piece, f is 1. And on this piece, we're integrating where f is 1, we're integrating sine m pi x over 2. So take the antiderivative, we get negative 1/2 2 over m pi cosine m pi x over 2. Plugging in the 2 and the 1, we get cosine of m pi. That, unlike sine, is not 0. So cosine m pi, again, is actually going to oscillate. It's going to go 0, then, I'm sorry, it'll be 1, -1, 1, -1, so on. And cosine m pi over 2 is going to do something very similar to sine. When m is 0, that'll be 1. When m is 1, that'll be 0. When m is 2, -1. M is 3, it'll be 0. M is 4, it'll be back to 1. So it's going to oscillate between 1, 0, and -1. All right, so now that we've computed those integrals, f then is, again, this is the formula for the Fourier transform, and plugging in what those coefficients are, we get a 1/4 plus, and I just plugged in the formula we derived for a sub m right here times cosine m pi over x, and then the formula we derived for b sub m right here times sine m pi x over 2. I simplified this a little bit, but other than that, those are the formulas we have. So, I mean, this is another way of writing the same function. Seems a little bit odd that we have this function that has this big jump in it that we're going to represent in terms of frequencies of sine and cosine when sine and cosine are continuous, and this is definitely not a continuous function. So it seems odd that we could even try to do this. And in fact, when Fourier first announced that you could do this, he was ridiculed for that very reason. People said, look, sine and cosine are continuous, the function you're trying to use is not, this is ridiculous, this will never work. Anyways, turns out Fourier was correct. All right, so what does all this mean then? I'm going to use Mathematica, a nice little piece of math software here. And I'm going to do the exact same thing that we just did, but I'm going to have Mathematica actually compute all this stuff for me. So I'm asserting here to Mathematica that P is 2. Hang on a second. Sorry about that. I paused for a second to make the font a little bit bigger so we can read this. All right, so I'm going to write some Mathematica code here. I'm going to trace you through this code. You don't need to know how this works, but I think what happens in the end is important. So I'm asserting here that P is 2, and then I'm defining that function f. So I'm defining it to be piecewise, and I'm saying it's 0 for t less than or equal to 1, and it's 1 for t in between 1 and 2. And then I'm saying that t is restricted to the range from minus p to p. This y min and y max, you don't need to worry about that. That just helps control the way some plots are going to look as we go down below. And then I'm going to compute a0, so that we're going to integrate the function f. Remember, this is a 0 function, so we just integrate, 0 frequency. We're just integrating f from minus p to p, and then we divide that by p. And then for am, I put simplify in here. Turns out it doesn't work for a reason I'll explain in a minute. We integrate, remember, we integrate the function f times a frequency of cosine, so cosine m pi times t over p. We integrate that from minus p to p. And then we divide that entire integral by p. And bm, similarly, we do the same thing except for sine instead of cosine. Again, we're integrating from minus p to p, and we divide that entire integral by p. Now, we're going to define then the function capital F, which is going to be the Fourier transform of little f. But it's not going to be the full Fourier transform. The full Fourier transform sums from 1 to infinity. We're only going to sum from 1 up to some number n that we're going to give. So we're going to do like a partial transform in some sense. And the partial transform is, it's a0 over 2 plus the sum, the coefficient a sub m times the frequency cosine m pi t over p, and then b sub m times the frequency of sine m pi t over p. And then this is just saying I want to sum from 1 up to n. So that's exactly the same formula we had right here. The only difference is m is going up to some number n, which we're going to say is 3, 4, 5, 10, 100, whatever we want. Okay? And then what I'm going to do is I'm going to print out this function f for various values for n. And then I'm going to plot that. I'm going to plot the original function f, and then I'm going to plot the Fourier transform of f. And the original function is going to be plotted in black and thick, and then the Fourier transform is going to be plotted in some other color, ranging from pink to blue. So let's see what this looks like. Now, first of all, this prints out those coefficients. So it computed A0 right here. All the lines that it ends with a semicolon, it won't print out. So the first line it prints out is A0, and it gets a half, just like we did. Then it prints out A sub m, and it gets the same formula we did, but it turns out it's tricky to get Mathematica to simplify sine m pi, because you have to convince Mathematica that m is an integer so that it can figure out that sine m pi is 0. And I kind of played around with that a little bit and then said it's not worth the effort. I gave up. And then b sub m is here. And then remember, this is the function f, so this is just printing out what f is, and this looks like the formula for the Fourier transform, right? A0 over 2 plus a sum from 1. Again, this isn't infinity, this is up to m, n. A sub n cosine m pi t over p, b sub n sine m pi over t. So this is that function, capital F, the Fourier transform. Okay, so now we're going to do the very first one where we're only going to sum from 0 to 0, which means we're not going to get any term. I'm sorry, we're going to sum actually from 1 to 0, which means we're not going to get any terms at all from the sum. All we're going to get is A0 over 2. And A0 was a half, so A0 over 2 is 1/4. So what does that do? Well, if you look at this function, here's a graph of f. 0 from -2 to 1, 1 from 1 to 2. So that function is only 1 on 1/4 of its domain, right? 1 from 1 to 2, that's 1/4 of the entire interval from -2 to 2. So if you think about this function as having a mass or an average area, the average area or average mass is 1/4, and that's exactly what that is, that 1/4. So we're going to shift up by 1/4. So we're shifting up to the average of that function over that interval from -2 to 2. And then we're going to sum up, we're going to sum from 1 to 1. That's this right here. This is saying I want n here to be 1. So we're summing from 1 to 1. And when you do that, here are the first terms in that sum for the Fourier transform. So now we're going to get a frequency of cosine and a frequency of sine, plus that original 1/4. And this function then is starting to bend to look a little bit more like this, but obviously we have this huge wavy part here that doesn't really look flat, but we can see that we sort of bent up here to get to this peak instead of being flat. So this is what happens when you throw in the very first frequency of cosine and sine. You get a very rough approximation for the original function. Now I'm going to throw in another set of frequencies. So we've taken now a sum from 1 to 2. So we've set in the next higher frequencies, and notice we start to get a little more detail. So this thing's now peaking up and hitting here, and it's kind of flattening out here a little bit. It's got more oscillations, but the oscillations are less, right? And then we get this jump up and we get this nice little peak here. So this is actually starting to look a little bit like the original function. Notice that this is a series. It's a Fourier series, like a Taylor series, but it's very different from a Taylor series in the way it behaves. For a Taylor series, you expect the approximation to be extremely good at one point, and as you move away from that point, the approximation gets worse. With a Fourier series, this is not a very good approximation at all, but as you add more terms into the series, the approximation gets better, but it gets better everywhere sort of at an equal rate. Okay, now we're adding in more terms. So now we're summing up to 3 in that Fourier series. And you can see the approximation is getting better. The oscillations here are getting smaller. We're contributing higher frequencies, but with those higher frequencies, we also have that the amplitudes are less. So we're getting less amplitude and higher frequency. And this is the higher frequency for the cosine. Okay, so we get this going on here. And the approximation is looking better. And then this is one more term. So, no, I'm sorry. In the very last one, oops. Oh, that was silly. I did 3 twice. 0, 1, 2, 3. Let's put a 4 here. In the very last one, I went 10. So this was with 4. I get the green. Notice the approximation is looking pretty good. We got an overshoot here, which you expect to have happen. And then when we get to 10, yeah, not bad. Okay, so these are the way Fourier series work. As you add in more and more terms to the sum, so now the sum's getting quite long, and Mathematica is putting them together. You can see it's putting all the cosines together and all the sines together. As this sum, as you add more terms, you'd expect the approximation to get better, and you can see that it does. But you still get this oscillation around the actual function that you want. And just for giggles, I'm either going to blow Mathematica up here or this is going to work. Let's throw in 100 terms. Let's see how quickly you can handle that. Oh, not bad. Okay, so if we throw in 100 terms, well, there's 100 terms. I'll investigate that. That's not as good as I was expecting, but there you go.